Hi everyone, Laurent here. We are going to be doing sample problem 233, section 6.2.6, part 6 of the notes. We're asked to find the altitude at which the ISS travels, the altitude h above the surface of the Earth. Note that the ISS here is much bigger than it normally is. We'll consider it to be a point particle, and the radius of the Earth will be useful in a minute. But this is the situation. And here we have the free body diagram for the space station, the only symbolized again by this big circle. It's in orbit, so the only force that acts is the gravitational force due to the Earth. That's in blue here. And then we need to draw our set of axes to determine our directions. We have here axis R along the radial direction. I chose this name because I can choose whatever I want, and I can choose the orientation that I want. R for radial, because we're in gravitation and uniform circular motion, which means we will have a radial force, a radial acceleration. NY, because I needed a second one. So we drew the situation, we drew the free body diagram. The next step is Newton's second law. So considering only the one direction, since we only have forces in one direction, so that's going to be the gravitational force and here we have it. That's Newton's second law in R, and then we have the gravitational force from the Earth is equal to the mass of the ISS times the radial acceleration, and the gravitational force is the universal law of gravitation, which yields g(me), mass of the Earth, times mi, mass of the ISS, over r squared, the distance in between the two, center to center distance. This is important, and that is equal to the mass of the ISS times its speed squared divided by the center to center distance. I'll erase and continue on from this. So right from here we can see a couple of different things. We can see that the masses of the ISS cancel away. We don't care. And we can see that one of these r's, without even knowing what the value of h is, without having plugged it in here at all yet, we can see that one of those two cancels away. Remember that whenever you have Newton's universal law of gravitation, what's important is to have the center-to-center distance. For the ISS that we consider it so small, we consider it as a point particle. This point here, it's all of it. For the Earth, the center is, well, 6,000 kilometers down. The altitude is just this bit. We don't know what this is. We don't know what this big R is that we find in here. We do know RE here. And every time you have the Earth and you're trying to find the altitude, you'll need to consider the radius of the Earth in the center-to-center distance. By this construction, we can see that R, big R here, this center-to-center distance, is simply RE plus H. First, let's find an expression for R in here, and then solve for H. Solving for R here, we simply take R, put it on the other side, V squared, put it on the other side, rewrite, and then we need to use this thing here. So we have here, and that's it. H is equal to g me over v squared minus re, where me is the mass of the Earth, 5.98 10 to the 24 kilograms. V squared is the speed of the International Space Station around the Earth, that's 7.66 kilometers per second. G is the universal gravitational constant, 6.67 times 10 to the negative 11, and re is the radius of the Earth, 6.37 10 to the 6 meters. You plug all of these numbers and you get the following. Do all of this and you should get 428 kilometers, and that's part A. Part B asks us to find what the gravitational acceleration that the ISS feels, and that's the radial acceleration that is created by the gravitational force. That's it. That's all we're trying to find. And so we have a couple of different ways. From the free body diagram that we had earlier and Newton's second law that we got from that, we ended up with this. Now, as a reminder, all of this is just the gravitational force of the Earth. That's equal to the mass of the ISS times the radial acceleration. But that's it. We use Newton's second law to get to this. We can do one of two things. Either we go and find what r is, knowing h, we can plug it here, or we find what the gravitational force of the Earth is, divide by the mass of the ISS, or really just look at this bit. So whether we calculate v squared over big R or gme over r squared, it will give us the same thing. I'm going to pick the easier way because I can. But try both and see that you get the same answer. Just to see. Convince yourself that that's correct. That is the job of any good future scientist, really. We see that AR is v squared over r, or v squared over re plus h. We know v, we know re, we know h. We plug and play. If you found in part A the value of r on its own, and then use that value and the value of re to find h, fine with me. You can then just use that value in here and you get your answer. Plug in your numbers and you should get approximately thereabouts. For part C and D, we have the following. We have an astronaut that decided to go on a spacewalk, 100 meters out in space, outside of the space station, slightly bigger than the record. That's between 90 and 100 meters. I forget the exact number. And we want to compare, because we're in physics and we like to do things like that, we want to compare the relative gravitational force between the astronaut and the ISS and the astronaut and the Earth. So let's just see what's going on. We have an astronaut 100 meters away from the ISS. Both of those are at the same altitude, 428 kilometers from the surface of the Earth. And we have, of course, the radius of the Earth, just in case we need it. The forces acting on the astronaut, we're considering them separately, right? Just what the gravitational force is in between these two things and in between these two things. For part C, it is astronaut and Earth. Part D, astronaut and ISS. We need to find the gravitational force between the Earth and the astronaut. We don't even need to draw the diagram. We know it's going to be pointing downwards, and since we're only considering that force, and we know its equation, well, this is it. So okay. So, gravitational force between the Earth and the astronaut is gme over r squared, where me is the mass of the Earth, we know, ma is the mass of the astronaut, we're given it, big R is the center-to-center distance, re plus h, and g is the gravitational constant. Plug in your numbers, and you get 1,597 newtons. I'll erase and go for part D. Again, here we're looking at the gravitational force, and well, that still has the same form. It's the universal gravitational force. It doesn't matter what the two objects are. They can be planets and stars, stars and stars, galaxies and galaxies, or human and human, or human and space station. It will still have the same form. So we will have the gravitational constant, the mass of the astronaut, 185 kilos, the mass of the ISS that we're given, and D is this 100 meters. We plug in our numbers, and once we have that, we should get 5.18 times 10 to the negative 7 newtons. And that's it. Congrats.